we're going to move on to a presentation by Ben Reuter and Sasha Belair. Ben Reuter is a researcher as well as an active avalanche practitioner. He spent the last several years at the Swiss Institute for Snow and Avalanche Research in Davos, Switzerland, doing research on variations of snow instability, as well as at Montana State University in Bozeman, looking into how weak layers fail. He's currently working on a project on climate change impact at Petro-France in Grenoble. As a mountain guide, he shares his passion, trains aspiring guides, and hopes for snow. Sasha Belair is a meteorologist who stuck his nose into the snow for his graduate studies at the Swiss Institute for Avalanche Research in Davos, Switzerland. In more recent years, he focused his work on coupled snow cover and numerical weather prediction models, working in Canada, Austria, and again back in Switzerland. Sasha is currently working at the Swiss Weather Forecasting Service, working on high-resolution weather forecasting in complex alpine terrain where snow, obviously, can never be neglected. In this talk, Ben and Sasha will outline the latest research on regional climate scenarios and how the regional changes can affect avalanche formation. This is a really important and, dare I say, a hot topic. So over to Ben and Sasha.
Well, thanks, Bruce, for the introduction. And I hope you guys can see my screen. And if I don't hear anything, anybody screaming, then I just will continue talking a bit about what we were asked to write down in a chapter of a book actually last year. And by we, I mean Ben, Christoph, and myself. Christoph would have been here, but he recently got twins, so all hands on deck for him, I guess. So this is really work in progress for us. We wrote it down in our thoughts on that one. And because this is work in progress, we also asked Simon to provide some data from Canada, and Ben will talk about this later on during this talk. So this is really work in progress, and we have some thoughts on how to tackle this problem, or how to do, or how to predict what is going to happen with avalanche in a changing climate or in changing environments. So sorry for that, technical problems here as always. So I'm pretty sure everybody has read or some of these headlines or similar headlines during the last years, and I just realized earlier that I picked this article by Devon, who talked earlier in the session, just by chance, so I hope I referenced this correctly. I'm not sure if Devon is still on, and I hope it's okay to use this in this talk. So we have seen all similar headlines like this. So, and we have to ask ourselves if we really have to carry our skis a hell lot often than we used to. So will there be less snow, or will it be the complete opposite? Will there be extreme winters? Will there be enough snow that we can even get out to ski because it's simply too dangerous? So summing it up, our ski holidays ruined all the time. We ski slopes like this here on the right side. So artificial snow with green size and maybe cows on the side. So will that be the scenario for the future? The main question is what will happen to our snowpack? And I would like to start with some background here, and we all, or most of you probably know that, but there are different snow climates already. So we have different snowpacks, and we try to illustrate this here with this little sketch here. And the most pronounced snow climates being a maritime or the continental climate on the other side. So being identified or characterized by mild winters on the maritime climates to more cold winters. This is obviously relatively speaking, with the maritime climate having more snow, but also some rain. And on the other side, in the continental climate, shallow snow covers. So which also means we have more persistent layers or persistent weak layers. And in the maritime climate, we have more short-lived weak layers. So different regional climates have been there all the time. The general question is, what will happen to these climates or in these climates? So we all know that without snow, we won't have an avalanche problem. So when we wipe out all the snow within the next 100 years, so we can just start biking. Probably most of us with electric bikes, but we still get out. So this is a study from Christoph Marti and others from 2017. They tried to figure out what would happen with the snow cover, and this is for the Alps. They analyzed this for catchment, or did some scenarios for a catchment in the Alps. So what you see here is the probability of snow cover, and this means what is the probability of having at least 30 centimeters of snow on the ground. And the green colors, or the color coding in general, means green, we have this 30 centimeters for over 100 days on the ground. Orange colors mean for 40 to 100 days, and red means for less than 40 days. So a little bit over 1 month. So if we start today and analyze this, we can see that down to about 1,800 meters, and they also separated this between north and south facing slopes. Below, or let's say above 1,800 meters above sea level, we have 100 days or larger than, or more than 100 of days of snow cover. And below that, it gets a little less. If we project this into the future, so they aimed at 2100 the year, we see this changes a bit, and basically the snow line rises a bit. So we see the 1,800 are barely below 40 days, and we still, but we can still see some greenham here, and this is good. And at least in the Alps, this means our starting zones will have snow, which is good, I guess, in terms of skiing at least, but maybe not in terms of avalanches. We will see that. We also know that extreme events create natural hazards, and there also have been a few studies, again for the European Alps here, where they found that extreme precipitation in the Alps will be more frequently and more intense in the future. And in terms of extreme snowfall, it looks like, or the studies showed that there will be more snow at high elevation, which is actually shown by these graphs here up here. So that's the probability. They start from a control run and apply scenarios, which will be the red line. And the ideal temperature range for precipitation, or for heavy precipitation, is between -2 and 0 degrees. So this blue line shifts with the scenario to exactly this range. If we go below tree line, so further low, we also move a little further into the warmer temperatures. It also means we have rain low, but we also can have this in high elevation, because this general curve moves out of this range. So the main ingredients for avalanches is that snow is there, and that means we have a problem. And in more specific words, we have probably avalanche problems. But the question is more, it's not if we will have snow in the future or not. The question will be more when or where, and especially what type of avalanches we will have in the future. So in other words speaking, what kinds of problems we are going to have in the future. So how are we figuring that out? So for starters, well, we can look at single manual profiles. The problem with these is we have to look, we need them from long time ago. I'm pretty sure each and everybody of these in the industry can dig up a profile which is decades old. But you find one from the early, let's say 30s or 40s, and then we have one or two profiles there. So we have not a complete record. We have incomplete records at each and every field site. We also have varying locations, because we are not digging the profiles in just one specific spot all the time for decades. We just want to figure out what's going on in our terrain. Over these long periods, we also have different observers and different standards. And in the end, we also need to predict the future. And the only chance we have there is to use models. And most of you, or a few of you, know me by now, and I'm kind of like the modeling guy. So we kind of like want to propose, or what we think we have to do is we have to combine snow cover modeling and snow instability modeling, some stuff that Ben will talk about later. In terms of snow cover models, others and myself have worked on that. We have these snow cover models, and you can see a simulation of the winter season here on the right side. So colors indicate different grain types. So everything is there that we need. And we can force them with either weather station data to learn about the past, but we can also force them with weather station data. And especially we can also force them with climate model output. Because it's very important. It's not only what is on the ground, it's also the interaction. And JT's talk earlier showed that, for example, the flow regime might change if the air temperature changes. So all these interactions are very important, but we need to not only look at the whatever, let's say +1.5 degrees. We need to look at the entire interaction between the snow cover and the atmosphere, because we all know the weather, the avalanches are controlled, the snow cover is controlled by the weather rather than the climate. And also what we have in these simulations are our weaknesses. So we know what kind of weak layers we have in there, which we can then identify. And the snow instability modeling here, we can consider different release processes, like natural wet snow avalanches or artificial release of dry snow avalanches. But what we need to do is we need to know how relevant these problems are, and their stability indices become in handy, and we can calculate these from these simulations. And for this, I want to hand over the presentation here to Ben. And I try this real quick here. Change the presenter to Ben, and he will take over and tell you more about our thoughts.
Okay, so as Sasha said, we want to be able to work with a long time series of meteorological and snow-covered data. And that means we need to work automatically. We can't go through all these profiles. And in the next, on this slide, I want to explain to you how, I want to give you one idea how to deal with this problem. And actually for every day that we have data for, so every day in the database, we actually need to do two things. We need to detect new weak layers, because weak layers form at some point in the season, and we have to keep track of problems. And keeping track of problems means we have to ask the question, what is the existing weak layer type? So this is the first column here. Once we found a weak layer and detected whether this is persistent or non-persistent, or maybe deep persistent, we can think about, is it a relevant weak layer? So is the slab thick enough, or has load been added? And these questions, they will be specific to the weak layer type. We want to assess the stability of the weak layer, and based on this assessment, we can actually decide whether we keep the problem for the next day or whether we might be able to drop it because it's not relevant anymore. And there's a second loop coming up at the bottom of the slide, And this is about detecting new weak layers. So has a new persistent weak layer been covered or just formed at the surface? Is there a new non-persistent weak layer that is relevant? And for relevance, we will look at the burial depth or the slab density indicators that describe slab and weak layer. We will also use stability indices to assess the stability and take a decision whether we keep it or we drop it. And for persistent weak layers, as you can imagine, they are persistent, so they will stay in the loop, whereas the non-persistent problems, they might drop out after 1, 2, 3 days based on those stability indices. What kind of stability indices are we using? And so far we decided to use we decided to follow the modern picture of avalanche formation. So for persistent and non-persistent problems, we use the damage criteria, failure initiation criteria, and crack propagation criteria. And we would also like to use in the future criteria for dynamic crack propagation, but this is still something that is in the works. For deep persistent problems, we will look at initiation, propagation, and also in the future incorporate here dynamic properties. So let's go back to this example that Sasha showed in the beginning of the talk, where we have 2 different snow climates. The mountain on the left, this is a maritime climate, and the mountain there in the back, this is now an example of a snow climate with a more continental, influence. So on the left, this could be Whistler, and on the right, this could be Mount Fidelity. And here is the application of our stability algorithm. So on the vertical axis, you see the avalanche problem frequency. So how often is an avalanche problem observed? And you can see here for both locations, left Whistler, right Mount Fidelity, the years from 2016 to 2020. So it's only 5 years of data that we're looking at here. And Simon ran those snowpack simulations, and based on his snow cover simulations, we produced those bars that are a bit in the background and have these pale colors. Those bars that are more in the front and have those bright colors, they are the observed avalanche problems that we took from the records. The colors follow the typical snow grain classification. So light blue is a persistent avalanche problem. The green will be precipitation particles, so it would be a new snow problem or a storm snow problem, and the red indicates melt forms, so this is the wet snow problems. We cover in both situations a time period from the 1st of December till the end of March. And from these graphs here, we can actually see that the algorithm picks up the differences between these two snow climates. So on the left side, we see a large proportion of storm snow or new snow problems and a lower proportion of persistent problems. And we also see in the middle of the winter season, we see some wet snow problems. On the right side, we don't see any wet snow problems when we see a higher proportion of persistent problems, which is typical of a more continental influence that we have at Mount Fidelity. The algorithm also represents the fluctuations that we see in the observations. So if we compare those bar graphs that are in the back and the bar graphs that are in the front, they look quite similar. They're not identical, but they look quite similar. And that gives us some confidence that we can pick up the fluctuations that are relevant to describe climate characteristics. So now let's change the location, look at another example. And this is an example of a transitional snow climate. So it's an inner-Alpine region in the Alps. And we're talking here about Weissfluhjoch, Davos in Switzerland. The elevation is about 2,500 meters, and it's a location right in the center of the Alps, a bit sheltered from the bigger storms in the north and the bigger storms in the south. And we see here a time series of profiles covering a period of 18 years, so from 2000 until 2017. And we always see the snow profile on the 15th of January, modeled with a snow cover model. And the snowpack runs were performed with meteorological data. So the data measured in the field at a weather station was used to drive the snow cover model. So again, here, the colors that you see on the profiles, they indicate the grain types. And so blue colors will be persistent, dark blue is a depth hoar, the dark red is a mild refreeze crust, the pale red is rounded grains, and the green colors, they are referred to precipitation particles or decomposing fragmented particles. And what is striking here is the variability between the seasons. So just about looking at the snow depth, we really see big variations. We see 1.50 meters. The next year, it's just a bit more than half a meter. And but we also see strong variations within one snow profile. We have strong layers, crusts next to weak layers, and those characteristics are really typical of transitional snow climates. Just based on this snapshot on the 15th of January every year, we can't really tell how the winter went. We can't really tell how the winter unfolded, and did we see many persistent problems, or did we have a lot of fresh snow problems? But this is just a snapshot, and we have the whole simulation behind, so we can actually track the layers. So now we choose one year, we choose the winter 2014-2015, and I show you with one example how we do the tracking. But to look at a weak layer and to look at its relevance for an avalanche to become an avalanche problem, we can look at failure initiation and crack propagation. We know that these two properties are very relevant for the stability. And here you see in the horizontal axis, I will put the failure initiation criterion, which compares the strength and the stress due to additional loading. Strength of the weak layer and stress due to additional loading. Low values of this criterion mean it is likely that a failure can occur. High values of S indicate that a failure is less likely. On the vertical axis, we have the critical crack length as a criterion for crack propagation. And short critical crack lengths, they indicate that crack formation, that a crack is likely to become self-propagating, and high values of the critical crack length, so it would be values of about more than 30 centimeters or 40 centimeters, means it is rather unlikely that a crack will turn self-propagating. So now let's put in the data here. The color bar shows time, and this weak layer that I'm going to present here is a weak layer of facets that has formed the 26th of December. This time, the weak layer was on the surface, and there was no slab yet. So it doesn't show up in our algorithm because it's not an avalanche problem yet. But until the 31st, more snow has been added and a healthy slab has formed so that it was an avalanche, so it became an avalanche problem. Over the next couple of days, the snow settled a bit and the weak layer strengthened a bit, so the crack length dropped. But then, you see it by the long red arrow, stability drops. And this was due to another 25 centimeters that fell in the night, 3rd and the 4th of January. And we see here the critical crack length drops and the failure initiation criterion increases. Failure initiation criterion increases means it's getting harder to trigger this layer because it's further down. but the critical crack length drops. That means stability, and this part of this side of stability decreases because of the increasing load. Cracks tend to propagate more easily. One day after, on the 5th of January, many avalanches were observed in the area. That's due to artificial release being recorded a day later, or lack of visibility on the 4th, just after the storm, when it was still pretty cloudy. So now we can draw two thresholds, a threshold for crack propagation and a threshold for failure initiation. And you will see that in this box on the left, this is what we call an avalanche problem. So a weak layer and a slab that poses a problem. So now we can go ahead and look at the avalanche problems over this period. So from 2000 to 2017, we have this graph here showing persistent, blue, and non-persistent problems in their frequency. So how many days did we count with our algorithm? And we also see with the red circles the onset of the spring wet snow avalanche cycles. And this refers to the right vertical axis where we see the dates. So we see a fluctuation of those persistent problems. Some years we have more, some years we have less persistent problems. We always have some non-persistent problems, but not many, which is typical of a transitional climate, such as the snow climate of Davos. This period of data is pretty short, and we can't really conclude on climate trends here. But I would like to still wanted to show you this slide, because I think it is interesting to see how this algorithm works, and that demonstrates that we actually get a quite reasonable picture and can actually characterize the nature of avalanche danger from numerical weather output data coupled with a snow cover model. But still, there's one little conclusion we can make here if we look at the wet snow avalanche cycles. And over these almost 20 years here, we see a trend. The wet snow cycles start about 2 weeks earlier. So let's look at the general conclusions. And as Sasha said already, we believe that it's not the right question to ask what is the influence of a 1.5 degree temperature in a global temperature increase on avalanche activity. We believe we should really use snow cover modeling and snow instability modeling to take care of those interactions of the snow cover and the atmosphere. Using those snow cover model data and those snow instability data is possible if we have the right tools. And we are working on that, and we are together with our colleagues in Canada, in France. We're trying to work together to have the right tools to actually tackle this problem and to really look at long time series of climate data and to be able to describe those fluctuations for avalanche activity. What we've also seen at the beginning of the talk is that those ingredients for avalanches, that means severe weather, severe changes in the weather, and just simply snow, will still be there in the future. But less snow will be available at lower elevations, and weather severity may actually increase. So looking now, zooming in on the Alps, and here we have a little synthesis of other studies that have been carried out in the past. We can describe the following picture. At lower elevations, we can use observations of avalanche activity to study the changing characteristics of the avalanche hazard. And what researchers have seen so far is that avalanches run shorter and are less frequently observed in those common avalanche paths in the French Alps, where they have a large database and a really pretty much complete observation of those traditional or typical avalanche paths, they also see that deposits are more often wet. But that does not mean necessarily that we have more wet snow avalanches, because those avalanches that have a wet deposit might have still started as new snow avalanche and new snow fractures at the top of the mountain. If we look at higher elevations, data is sparse, and the picture that we get is not as clear. Also, the snow cover thickness and the new snow amounts, they persist, so they stay about the same, and they might even increase a little bit. And the latest simulations we have from those regional climate models, they see this trend to more severe weather and more heavy precipitation events. Most recent snow cover model results, they indicate a decreasing avalanche frequency, but this is a result, I think, that needs to be confirmed in the future with more recent regional climate model data. And it will be interesting to find out whether we see the same picture, that the whole avalanche activity decreases or not, or how different types of avalanches, new snow avalanches at higher elevations or wet snow avalanches at lower elevations, will behave. From our very short analysis with limited data here, we've seen that those wet snow avalanche cycles come more early now, and about 2 weeks per 20 years in the inner Alpine valleys, and we can conclude that on this short period of 20 years, persistent weak layer problems have not become more frequent or less frequent, which was a question often posed by practitioners. Well, those are the small conclusions we can make so far, but we're gonna be back with more soon when we are able to apply these tools that we're currently developing and can actually look into longer time series of climate data. And here is again the book chapter that we've been working on with Sasha and Christoph, and so far it's been in German, and I hope that we have a proceedings paper next year for Fernie, and that summarizes this whole book chapter, and we can also be back with some more quantitative data on the future of the avalanche activity in those in our mountains. Thanks for listening, and I would like to hand back to Bruce.
All right, thanks very much, and thanks for making the distinction between trends in the averages and the some trends in the extremes. We'll just take one quick question here, and then we'll move into our wrap-up. Do we have any? Okay, Olivia doesn't have any questions in the chat box. Do we have any live questions, Brent?
We have no questions from the floor, Bruce.
Okay, all right. Well, that's great. Thanks very much to the today's speakers. We had a really wonderful mix of practitioners, researchers, and people who were both practitioners and researchers, and a really wonderful variety of topics and presenters. So thanks all for a really valuable session, and I'll hand over to James.
Thanks, Bruce. And thanks to all the speakers in the last session. It really was a phenomenal session and a phenomenal conference. So just bear with me for one small second here. And I just got a couple of reflections just before we leave the conference here from a random selection of the talks. We learned that when you're trying to show off to somebody, or maybe you're feeling horny, then that's more likely to reinforce any risky behavior that you might be undertaking. We've learned that we can probably expect benefits of empowering all members of a team to take initiatives, even though formal communication structures are still relevant and have their place. And we're thinking over the implications of moving around the mountains with our GPS tracking devices and how this can allow us to monitor in real time decisions we make when we're moving through the mountains. So as far as the discussion panels goes, the mentorship discussion panel really reinforced how important that side of what we do is. You know, I'm reflecting on the snowmobile discussion panel, wondering if we are at a watershed moment of some kind, at least in North America, where snowmobile travel and risk mitigation methods associated with snowmobile travel become mainstream within the avalanche industry. Finally, Bruce's comments really resonated about the importance of case studies. And for me, at least, those were such a great highlight. So thanks once again to all the speakers, all the panelists, and all the poster presenters for all your hard work. It really is appreciated. Your contributions make the VSSW what it is. One final reminder, you can watch all of the recordings of the presentations by clicking on the links from the presentation website. Although please be patient and wait for today's videos to be processed, and we'll get those up to you for tomorrow. So I'm personally a big fan of fingerless gloves for a very good reason, because they shorten the time between work time and being outside. So with that said, I have a ride to go on, and I'll just pass over to you, Steve.
Okay, thanks, James. I guess to start with, I'd like to begin by acknowledging that we have gathered here on the traditional territory of the Ktunaxa Nations, and we would like to thank them, as our mayor did at the beginning of this event. I'd also like to thank the VSSW 2020 sponsors, and say that they gave us the support we needed prior to the event, and that's probably the most important part of it. For us is you're going out on a wing and a prayer kind of in the beginning of these sorts of new ventures, and so a really big thanks to those guys. As mentioned, the ISSW 2020 has been rescheduled to 2021, and we'll be rolling out the updated information in the coming months, but rest assured that we will be there in full force as well. So I'd like to thank the ISSW 2020 sponsors as well, and their continued support. So again, you know, with all the changes that have been coming about and things in the future, we'll be relying pretty heavily on them in the beginning as well. I want to now talk briefly or touch briefly on some of the early Elk Valley avalanche history before I let you go. The first records of snow and avalanche fatalities in the area were really just around the corner here, a short distance away from where we are broadcasting today. In Coal Creek in 1912, there was 6 fatalities, and again at the very same work site in 1913, there was another single fatality. I'm hoping that since that time that we've learned a lot and we're not making the same mistakes over and over again, and the ISSW and the VSSW are helping to support that. My first memories of avalanches in the area were from 1979 event that took out the 1-year-old Grizz chairlift that was just over here. And as you can imagine, this event sent a few shockwaves through the resort and doubled up the pro patrol from 2 people to 4 people that year. The ski area hired an expert from Rogers Pass to lead the team. His name, many of you will know him, Dave Akins. Dave has been a very regular attendee of the ISSWs going way back to close to the beginning, if not all the way back, way before my time. Many of you will know him, and I'd really like to thank Dave for his life's work keeping skiers safe here in Fernie. Another character that was already on site during when that avalanche happened, he was teaching skiing here and switched over to the patrol about that time. I'd like to thank Robin Siggers for your contribution to Fernie and for moderating session number 1 on our first day of program.
Yeah, see you next year.
Our ski area in Fernie has produced a significant number of avalanche specialists, and we're very proud to also have Mark Vesley here to help us and moderate session number 2. He couldn't make it; he had some family things to attend to, but you know, big thanks to Mark as well. Some people outreach most of our imagination and take their work in directions we have trouble imagining, and Jen Coulter is one of those people. She moderated session number 3 and is one of the people from Fernie that I'd really like to thank. Thanks, Jen, for your work here and all that you do. Moderating session number 4 was Bruce Jameson, who needed no introduction to this group. What's interesting for me is, as mentioned earlier, is that he first patrolled here in Fernie, and this kind of completes the circle for our moderators, all having started their Avalanche careers here in Fernie. I'd also like to thank our 2 chat monitors, who were big helps in the background here, Nicole Maddie and Olivia Johnson. Olivia helped set up this location here at the Elkview Lodge as well. Mary Clayton, Christine Grimble, Mark Gallup, and Claris Media all helped with the communications part of the VSSW. And you can imagine with a new event and all the changes that were happening, this was a lot of work, and I really appreciate everything that they've done. Behind the scenes, in charge of registrations was Tyler Carson and Sue Boyd, and this was a huge job. And in fact, they worked really hard over the last couple of days. We're trying to help people through all their challenges, logging on and stuff like that. It's a bit of a cliche to say this, but we truly could not have pulled this off without Brent Strand, our technical producer. And whoever said that we're all replaceable, they got that totally wrong. He, for one, is not even close to replaceable for many reasons. I'm sure you would all agree our poster sessions and the presentations were innovative, broad-reaching, and interactive. And I really thank Simon Horton for doing an amazing job with that. We had a great platform. Thanks, Simon. This was an outstanding program. James Flory, he's one of a kind, a top-notch scientist, open-minded, innovative, and above all, dedicated and hardworking. Thanks, James, for all you've done.
See you in 2021.
And your patience with me, too. Thanks. I can't tell you how proud we are of the work that we've done here to put on this event, but I can tell you it will seem even better with a bike ride and a beer. So have a great fall and a safe winter, and we'll see you all in October 2021 at the ISSW.